Girls, let's talk about piecewise functions from page 10 of our noties. What's a piecewise function? A piecewise function is one in which the rule may take a different form over different sections of its domain. So it says that over a domain, which remember is over your x phase, it may be made up of various different functions. Let's look at the first example. State the hybrid functions present in the graph below. Well, if you look at the graph below, you'll see that there are three different functions. So together it makes up a piecewise function, depending on, it's made up of three different functions because it's got three different graphs going there over three different domains, which means three different values or limits of x values. The first one going from left to right looks like this one. So this red one with an arrow on the end looks to be starting at x is equal to 0 and then progressing to the left, which means that it's including all the values of x that are less than 0. Now, if you look to the right-hand side, that's described by this section here. So fx refers to y equals. And then we've got three lines for three different functions that make up the piecewise. The first one is the one that we just looked at for values that are x less than 0, as it says. So being less than 0, not equal to or less than 0, above 0 on the x-axis, that line starts there and it's got a dot above it, not a filled in. So we're talking about just this first section, first line of the piecewise function on the right hand side, first graph on the left hand side as you go from left to right. Now, what is that function? What's the rule? Well, I'm sure you can tell that it's a line, isn't it? It's a linear function. So what's a linear function made up of? Well, we all know that it's of the form y equals mx plus c, for which you need a y-intercept. What's the y-intercept? So where does this first line cross the y-axis? It crosses at y is equal to 1. So that's the value of c in our general formula, y equals mx plus c. General form for a linear function, it goes y equals mx plus c. C is the y-intercept. This one crosses the y-axis at 1. Its y-intercept is 1. What about the gradient? So the gradient is the value of m. And for this, we need a rise over run. So if I take this point there and that point there, both on that line, the rise between those 2 points would be 1. And the run between those 2 points would also be 1. So the gradient is rise over run, 1 over 1 is equal to 1. So the y-intercept is 1, the gradient is 1. Therefore, the equation for that straight line is y is equal to 1x plus 1. So we're going to use that and put that into the notation which is on the right hand side of the page there. Okay, remember fx is just referring to y. So for the first line, y or fx is equal to 1x plus 1 or x plus 1. There we have. So that's the first portion of our piecewise function. For values of x less than 0, we have the function y or fx is equal to x plus 1. That's the first part of the graph as you go from left to right here. Now in the middle you've got this section which according to our notation on the right hand side is y is equal to x squared. That's the curve there. It's your typical parabola. Now look at the x phase for which it goes between. I would think that it goes between x is 0 and x is 2. And being that there's dots, filled-in dots in each of those end of that line segment, I think that all our x values would be between 0 and 2. So 0 is less than or equal to x, and x is less than or equal to 2. So that is describing the middle piece of our piecewise function for the parabola y or fx is equal to x squared between the values of x is 0 and x is 2, including both of those. So we say 0 is less than or equal to x, less than or equal to 2. Last bit. Now the last bit is this third little bit of our piecewise. Looks like it starts on the x-axis at 2 and heads downwards, which means that it keeps on going to infinity and including all the x values that would be greater than 2. So in my last little line here, what's the range of this thing? Or rather, what's the domain of this last section? It would be all the x values that are less than 2. Now, not less than or equal to 2, because again, at the start of that little, line segment, there's a circle, not a filled-in circle. X is equal to 2 is not part of this. So it would just be x is less than 2. And I've just seen my mistake. Of course, that's not x is less than 2. We're talking about all the values that are going to be greater than 2. So it means this line goes from 2 to infinity. It might be below the x-axis, but it doesn't matter. It's going to include all the x values that are greater than 2. So there we have our first piecewise function made up of 3 separate segment functions. Hence we call it piecewise. Now, just before we go into this last function, this last piece is y is equal to 2 minus x. Is it? Well, it would say, so if we had y is equal to 2 minus x, its y-intercept be equal to its gradient equal to -1. And if I was to take this line back, I'm sure it would cross over the y-axis at 2, and we know it's sloping downwards, so its gradient would have to be negative for a start. So I'm thinking we're pretty right in saying that, yes, this is the function y is equal to 2 minus x for values of x greater than 2. Now, if you were given values of, say, for example, 2, would the value of 2 be part of the inner function or the one on the outside? Well, in cases where there's a swap, where some value of x is overlapped by 2 different functions, okay, one will have to have a dot, the other one will have to have a circle around it. So it can only be included in one of those different functions in the piecewise. In this case, 2, value of x is equal to 2 would be part of the middle function, fx is equal to x squared. So for this particular piecewise function, for x is equal to 2, the value of y would be 2 squared, or 4. Let's go to the next example. Okay, sketch these. So we've got 3 different functions, part of my piecewise function. I've got fx or y is equal to 2 minus x for values of x that are less than or equal to -1. Another one, y is equal to 3 for values between -1 and 3, not including -1 and 3. And y or fx is equal to 2x minus 5 for values of x greater than or equal to 3. Let's look at the first function. So that refers to y is equal to 2 minus x. That's a linear function I hope you can recognize. Its y-intercept would be equal to 2, and its gradient, or value for m, would be -1. So that means that you would find this function on the graph at y is equal to 2. Mark that point, that's its y-intercept. And it's got a gradient of -1, which means that if you write it as -1 and 1, it goes, to find another point, it goes down by 1, over by 1. There's another point that would go through the line y is equal to 2 minus x. So I could draw a straight line through those 2 points. So here I've drawn on my graph the function y is equal to 2 minus x. Let's write that in. That's y is equal to 2 minus x. But the trouble is that I don't need all of this graph. I only need to draw this for values for x less than or equal to -1, which means starting at -1 and everything that is less than that. So on my graph, -1 is here. X is equal to -1 is there. And where x is equal to -1, y equals this bit. Now I need anything less than x is -1 and equal to, and anything else I don't require. So this graph that I've got really I should ditch it. Cut it. All I need is just another graph, but only from x is less than or equal to -1. So I might do this in pencil, but then come back and just ditch all the stuff that I don't need. So I only need to draw the graph y is equal to 2 minus x between values of comma x less than or equal to 1. So at one end I'll have an arrow, and at the other end I'll have a filled in dot where x is equal to -1. Okay, what about the rest? So that's the first portion. Now the next we've got fx or y is equal to 3. Okay, now that's between values of -1, we were just there, and 3. So when x is equal to -1, y will also be equal to 3. So where does y is equal to 3 look like? Well, it's a horizontal line that goes through the y-axis at 3, of course. So this case, we only need the graph, or we need the graph y is equal to 3. That's a horizontal line. I can use my I can use my shapes here to graph that. Here we go. So from x is equal to 1, all the way over to x is equal to 3. That's that point there. That's the bits that I need. Now, you'll see that the domain we're talking about is between -1 and 3, but not including those. So back on my graph, I can leave my line here, this middle line, this horizontal line, which is y is equal to 3, but I'll put a dot. Excuse me. Oh, no. So putting a dot on this bit here above x is equal to 3, which is included in as part of the line y is equal to 3. Horizontal line goes through 3 on the y-axis, and it goes between -1 and 3. And sorry, they're not included, -1 and 3, so I've done a typo. There shouldn't be a dot above. The 3 for this bit. 3 is not part of this function, so we put a circle. We put a circle around this portion above x is equal to 3. Right, there's our second line. Now the last bit is this, fx or y is equal to 2x minus 3. Now what do we know about that? Okay, sidebar. So this one, the y-intercept is -5. The gradient is 2, or 2 over 1. So to graph that one, we need to go down to -5 on the y-axis. 1, 2, 3, 4, 5. -5 is there. To find another point, we go rise by 2, run by 1. That's another point there. So I will have a straight line that'll go through those 2 points there. Let me insert a line that does that. Okay. Do a line between there and up here. Come on. There we go. Beautiful, beautiful, beautiful. Okay, there's my line. Now, do I need all of that? Let me just draw it out a little bit further. Do I need all of that line? I don't, because if you look back at the domain, it says we only need to draw this graph, y is equal to 2x minus 5, for values of x greater than or equal to 3. So when x is equal to 3, it starts at this point on my line. So I can draw another line in, which I will. I'll insert this line, starting from x is equal to 3, and going, come on. Oh dear. X is equal to 3 there. And this bit we'll put all the way up here. This other bit in here. Oh. Sorry, it doesn't want to play. This other bit I'll delete because I don't need. Now at this end of my last little line segment, this is for the function y is equal to 2x minus 5 for values of x that are greater than or equal to 0. So x is equal to 3 is part of this function. So for this last little line that I've just drawn, I have to put a nice big fat dot at this end where x is equal to 3. Okay, that means that 3 is included in the last part of my piecewise function, not the middle bit. So here's my three different parts of my piecewise function drawn between those particular values of x for the domain. So the first one is 2 minus x, and only for values of x less than or equal to -1. So that's what this is. And so I originally drew the original function y is equal to 2 minus x, but then just nuked out the bit that I don't need. I only need values for x less than or equal to 1. The second function is y is equal to 3. That's a horizontal line that goes through 3. And I needed to draw it between -1 and 3. Now, I draw that in between -1 and 3. Now, at both of those ends, there should be circles. And the reason why there's not a circle on this portion above -1 is because it's part of the first function, y is equal to 2 minus x, where -1 is included. And the last part, y is equal to 2x minus 5, so that's a linear function too. So I know where to find its y-intercept and its gradient, draw it in, but then just nuke the bit that I don't need. I only need values for x greater than or equal to 3, which is this section that I've drawn in here, and an arrow on the end to indicate it just keeps on going. The rest I don't need, so I don't put it in. Let's go to the next example. A continuous piecewise linear graph is constructed from the following linear graphs. So we've got y is equal to 2x plus 1 and y is equal to 4x minus 1. By solving equations simultaneously, find a point of intersection, hence state the value of a. Let's go down the bottom and do that. So I've got y is equal to 2x plus 1. That's a linear function, we all know. And another linear function, y is equal to 4x minus 1. Where do they intersect? Well, I can use substitution to do that. Sub 1 into the other. Substitution. Now, 2x plus 1 equals y, and 4x minus 1 equals y. So if they both equal y, they must equal each other. I can sub 1 into the other. So I can put in, I'll redraw the first function, y is equal to 2x plus 1, but instead of putting y is equal to 2x plus 1, I'll put 4x minus 1 is equal to 2x plus 1. Okay, now I've got one equation for which I can find the value of x. I could add 1 to both sides to make that 4x on the left-hand side and 2x plus 2 on the right-hand side. I could take 2x from both sides. On the right-hand side, that would leave me just with 2. And on the left-hand side, 4x minus 2x would be 2x. So 2x is equal to 2. X would have to be equal to 1. And if x is equal to 1, what's the value for y going to be? Well, I could put x is equal to 1 into either of my two equations. I'll try the first one. 2x plus 1 becomes 2 times 1 plus 1. And that equals 3. So, what does that mean? Well, that means that the point of intersection would be 1, 3. X is 1, y is equal to 3. And if I go back to my top here, and if I look at my domain that we're talking about, in both cases they feature A. In the first graph, y is equal to 2x plus 1, it's for values of x less than or equal to A, and 4x, and y is equal to 4x minus 1, x is greater than A. That value of A represents the x coordinate of their intersection. So that means that A in this case would be equal to 1. And we can use that to graph both of them now. So I know that there's a point of intersection at 1, 3, so it might be an idea to put that in first. Okay, x is equal to 1. Now, I'm going to graph both these, sketch the piecewise linear graph. So I'm going to graph the first one, y is equal to 2x plus 1 for values of x less than or equal to 1, and the other one 4x minus 1 for values of x greater than 1. First bit. Let's go back down here. So B. So if I'm talking about the first function, y is equal to 2x plus 1, it's got a y-intercept of 1, yeah? And it's got a gradient of 2, which will work better as 2 over 1. Rise of 2, run of 1. Let's graph that. So y is equal to 2x plus 1. It's got a y-intercept of 1. It's got a gradient of 2. So if I rise for 2 and run for 1, I get that point there. Okay, that's going to give me a lovely line through which I can draw those two. But I only need to draw this part for values of x less than or equal to 1. There's x is equal to 1. So my values, in this case, will only need to go between that point and this point. And everything else we don't need. So there's the function y is equal to 2x plus 1 for values of x less than and equal to 1. Now, it being x less than or equal to 1, at the end of this line, I put a dirty great big dot. Come on. Put a dot. There we are. What about the other bit? So the other graph, the other function, linear function is y is equal to 4x minus 1. So it would have a y-intercept of negative 1. It would have a gradient of 4, which would look better as 4 over 1. Let's graph that. So this time we start at negative 1 on the y-axis. Negative 1. We're going to go up by 4 and 1 across. So that is 1, 2, 3, 4, and 1 across. Well, we get to the same point that we had before. So this time we're going to draw a graph between those 2 points. And it's going to look something like 1, 2, 3, 4, 1, 2, 3, 4. It's going to go. It's going to look like between those points something like this. Good. 2, 3, 4. Look like that. But I didn't draw all the graph because I need to draw this one between, or for values for x greater than 1. So here's my x is equal to 1 here. The second part there, you'll see that it's not quite in line with the first section. That's because they're different functions. And I need to draw this this second function for values of x greater than or equal to 1. So here's my first part of the line of my piecewise function for y is equal to 2x plus 1. And here's the second part of my function for y is equal to 4x minus 1. Ta-da! And there's my piecewise function. Next one. Okay, consider this function. So it's a piecewise function, but this time only 2 different parts of it. There's fx or y is equal to x squared for values of x less than 1, or y or fx is equal to 2x for values of x greater than or equal to 1. So if I was to take the values and put into fx, what would they equal? For example, what would f of negative 2 equal? So in this case, we've got to work out where the value of x is negative 2 falls within our domain. Now, is negative 2 less than 1? Or is it greater than or equal to 1? Well, obviously it would be less than 1. So we need to put it into this first part of our piecewise function. It's going to be, so f of negative 2 would be negative 2 squared, following the first part, or the first rule part of our piecewise. Negative 2 squared would be 4. All right, what about the next bit? What about f is equal to 1? Now here's tricky because 1 looks to feature in both of our domains there. Now, is 1 less than 1? Or is 1 greater than or equal to 1? Well, in this case, the 1 falls in this part of our piecewise. X is part of x greater than or equal to 1, x being 1. So we need the second part of our piecewise function here, this time the 2x. So that would be 2 times 1, which is 2. What about the next bit? What about when x is equal to 2? Where does it fall in the scheme of things? Now, is x less than 1? Sorry, is 2 less than 1, or is 2 greater than or equal to 1? Well, 2 is definitely part of greater than or equal to 1, so it's the second part that we use for our piecewise here. To find the value of f2, we're going to go 2 times 2, which is 4. Cool, cool. All right, what about the next bit? Sketch the graph of f of y is equal to fx and state its domain and range. Domain and range. So that means graphing the stepwise function that we've got. Now the first bit is fx or y is equal to x squared. Now we know that's the parabola, don't we? And we know that we're talking about this at infinitum last term. Okay, y is equal to x squared has a turning point at 0, 0. It's got points through 1, 1 and negative 1, 1. It's got points through 2, 4 and negative 2, 4. It's got points through 3, 9. Let me find 9, 4, 5, 6, 7, 8, 9. So it's got a point through there, it's got a point through there. Now, if I was to join them all up together, I'd have the function y is equal to x squared, but I don't have to join all of them up because, as it says in the piecewise, we only need to draw this part for values of x less than 1, not including 1. So going to x is equal to 1, where are all the values of x less than that? Well, that would be to the left-hand side of this point here. So I'm going to draw in these points. At this end, I'll put a arrow to indicate that it just keeps on going to negative infinity. At this end, above x is equal to 1. Now, x is equal to 1 is not part of this function. So although I might have a little dot there, I should have above the 1 a nice circle not filled in and the rest of it joined up. Okay, so that's what y is equal to x squared for values of x less than 1 equals 2. Now the next bit, y is equal to 2x. So y is equal to 2x. So y is equal to 2x. What do we know about this? It's a straight line, yes? It would have a y-intercept of 0, and it would have a gradient of 2, 2 over 1. So start on the y-axis at 0, go up by 2 and over by 1. Starting here, go up by 2, 1 and 2, over by 1. There's a point, it goes through there. So a straight line will go through those 2 points that I've graphed here at 0, 0 and at 1, 2. So if I was to draw a straight line through them, let me see, it would go through something like this. Beautiful. Except I don't need all of that graph. I only need it for values of x greater than or equal to 1. Where is x equal to 1? Right there. So there's only a portion of that thing that I need. So I can go back and get rid of all that and just draw in this bit. For x is equal to 1. Start there, go through there. Like that. Now the last part of this question C states, state any value for x for which the function is not continuous. Well, although this is a function, if you were to draw a vertical line through any point on this graph, it would only go through one point. There is a break in the graph, and it happens at x is equal to 1. There's a little bit that's part of the parabola, and then a straight line takes over after that. So there's a break between x is equal to 1. At that point, we say the function is not continuous. It's made up of two separate functions, but overall the piecewise function we say is not continuous, and that happens at x is equal to 1. All right, Next and last example, we've got this. The following two equations represent the distance travelled by a group of students over 5 hours. Equation 1 represents the first section of the hike when the students are walking at a pace of 4 kilometers per hour. Equation 2 represents the second section of the hike when the students change their walking pace. So for the first part of the section, it says d is equal to 4t, and it's between values of t is 0 and 2. So if I had, for this first section, at t is equal to 0, what distance have they covered? Well, if I put t is equal to 0 into this, that would be 4 times 0. The distance covered would be 0. When I go to t is equal to 2 for this first equation again, at t is equal to 2, the distance traveled would be 2, or at 4 times by 2, the distance would be 8. As in the second section, we're going between t values of 2 and 5. When t is equal to 2, what distance will they have travelled? That would be 2 times 2 plus 4, which is 8. So again, I'm subbing t is equal to 2 into the second equation this time. And when t is equal to 5 at the end of the journey, what distance will they have covered? Well, if I go 2 by 5 plus 4, that gives me 14. Now I can use those numbers in the graph below to sketch what the thing looks like, what the journey looks like. But let's work through a couple of questions first. The variable d in the distance in kilometers from the campsite, t is in hours. What is the dependent variable? Well, as you would hopefully remember, independent variables are graphed along the x-axis, and dependent variables will be graphed along the y-axis. In this case, if I was to compare any of these graphs to y equals mx plus c, y is measured along the vertical axis. That makes it the dependent variable. In this case, d is measured along the vertical axis. It's the dependent variable. So in a graph of d versus t, d is the dependent variable. For part B, determine the time in hours for which the group travelled in the first section of the hike. Well, the first section of the hike was between t is 0 and t is 2. That means that it travelled, in the first section at least, they hiked for 2 hours. Part C, what was their walking pace in the second section of the hike? Well, you would hopefully remember from last year when we were talking about linear functions that the gradient is the determining factor about rates. And in this case, in part D, equation 2, distance is, well, they start at 4 kilometers at the start. That makes y intercept equals 4. But after that, for every 1 hour, they go 2 kilometers because the gradient is equal to 2. The gradient is 2 over 1, which means 2 on the vertical, that's 2 kilometers, over 1 on the horizontal, that's 1 kilometer. So what was the walking pace for the second section? That was 2, as in 2 kilometers per hour. For how long in hours did they walk at this pace? Well, that's what they did for the second part of our hike, and that was between values of t is 2 and t is 5. So how long did they walk between t is 2 and 2 is equal to 5? That would be a total of 3 hours. And last bit, sketch the linear graph for this. All right, well, we know that they intersect at the point. Where do they intersect? That's the point. Let me see. They intersect at the point t is equal to 2. When t is equal to 2, for both of those graphs, they've travelled 8 kilometers altogether. So there's our point. Now for the first section between t is 0 and t is equal to 2, that's that straight line between the origin and that point there. At t is equal to 5, they've covered a distance of 14, which is this point on our graph. So taking that point at 5:14 and connecting it to 5:14 and connecting it to the other point at 2:8, we have the piecewise graph for this hike, broken into 2 sections between 0 and 2 hours, and 2 and 5 hours there. That's better. And you can tell by looking at the second half of the hike, it's not at a bigger or faster rate than the first part. Anyway, that is piecewise functions. I hope you got something out of it, guys. We'll see you later.